draw this thing. So it's not continuous. Now, which part of the definition falls apart? Let's take a look. Does f of c exist? Yeah, it's right there. F of c equals a, the y value. That's the point on the graph. Does the limit exist? Does the limit as x approaches c of my function exist? Where are my fingers coming together at as I approach c? Oh, they're coming together at b. So I'm 2 for 2. The third part of the definition says that these two things have to be the same. They are not. So it's the third part of the definition that falls apart for us. The f of c does not equal the limit as I approach c. Or I should say as the function approaches c. So right there is why, explaining why it doesn't work, why it's not continuous. Okay. And that's not even on the screen anymore. Okay, next one. Nice little piecewise function. We'll put the hole here at A, point here at B, and we're going to put our C right there. So, obviously not continuous. So we're going to look at all three parts and talk about the why it's not continuous. So first of all, does f of c exist? F of c, oh, it has a point here at b. So f of c does exist, it equals b. Does the limit exist? If it does, what is it? Well, as I approach from the right, I get close to b. As I approach from the left, I'm getting close to a. So the limit does not exist. None. So it's impossible to talk about the third part of them being equal if the one doesn't exist. So right here, the part of the definition that's falling apart for us is the second part. The limit doesn't exist. Okay. Moving on to some problems like you're going to have in the homework. And these are the most challenging ones. We'll start easy to build your confidence. You have to sketch a function with the given conditions. So, example 2, sketch a function with the given conditions. Start simple. Make your graph continuous at x equals 3, and there's a cusp at x equals 3. Okay, so you're just drawing any kind of function you want. We'll go out to 3. I have to be continuous there, so it can't be a hole or an asymptote or a jump, and I have to have a cusp there. So it's just knowing what a cusp is on this one. A sharp change in direction. I would say maybe like, let's see if I come in like this, and then sharply change, come back down, swoop away. There it is. That's an easy one. Next one. I want f of 2 to equal 3. That's giving you an ordered pair. There's going to be a point there. 2, 3. It's going to increase slowly at 2. The limit as as x approaches 5 of your function is 6, but there is no f of 5 value. Oh, I skipped over another easy one in here. No, that's all right. So if you can get this one, this is always challenging as they get. There's a lot going on here. So let's take a look. We got a couple different spots on the graph to pay attention to. So we got something happening at 2, we have to have a point. And then out at 5, we've got some stuff happening. So 3, 4, 5. Okay. So first of all, I know that I have to have a point at 2, 3. 1, 2, 3. Put that there. And out at 5, the limit has to be up at 6. I'm going to get up to 6. But I cannot have a point at f of 5. So what do you think's happening there? I have to have a limit, but I have no point. So what's happening in the graph there? Hopefully you could come up with, there's a hole there. Because the hole lets you have the limit, but no value. Now I've got to increase slowly through 2. So increasing slowly, that's just coming real shallow, uphill curve, shallow, shallow. And it doesn't say what it does, so it doesn't matter. And there it is. I think I've met everything. I've got the point, increasing slowly, it has a limit, but no value. I skipped over an easier one in here, but I think you'll be fine. Okay, just an easy question for you, because you're that good. Is the function that's equal to x squared plus 5 over x minus 2 continuous without graphing it? And if you answer no here, can you tell me where? So first of all, is this continuous? Well, all you're looking for in a fraction is there any place where the denominator is going to be undefined? Well, yeah. If the denominator is 0, you got a problem. So that happens when x is 2. So it's discontinuous at x equals 2. But when I put 2 in here, I'm going to get, let's see, what do we get? f of 2. It'll be 4 plus the 5 over 2 minus 2. I'm going to get 9 over 0. I did not get that 0 over 0. Remember, when we get 0 over 0, that's that removable discontinuity. So I know this is not a whole. To get that step in the graph, those are piecewise, where you got separate equations that lift the graph separate from each other. The only thing this can be is an asymptote. So what we've got going on is an asymptote. Oops, spelled that wrong, didn't I? And if you're not sure, you can just graph it in your calculator, y equals, and you can see that there's definitely a vertical asymptote at 2. One last thing to do, and it's talking about the greatest integer function. So we want to explore, it's not really an example, the greatest integer function. And after we look at it, we want to see, is it continuous at 2? Okay, remember where this bugger's at. Go y equals, let's see, math, num, int, it is int, yep. So I went to, so math, over to num, down to int, number 5. Oh, but I gotta be in the y equals. Alright, try that again. Math, over to num, down to number 5, x. We're just gonna take a look at the graph, and then I'm gonna tell you what it's doing. Do a zoom, x. I want to get less of this in here so you can really tell what's going on. Window, I want to go, x, I'll go negative 3 to 3. Negative 3 to 3. Let's see if that looks a little better. Okay, it looks like a bunch of steps. Remember, the 83s connect here, and technically that does not belong there. So, I want to show you what's happening in a table. I want you to make your table go kind of an obnoxious table so that we can actually see what's going on. I want to go from 0, and I want to go by 0.2s. So 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, 1.8, 2, 2.2, 2.4, I'm kind of running out of room. Okay, let's set our table up the same way and see what the y values are. So go back, table set, starting at 0, and I'm going by 0.2. Okay, the y values. At 0, it's 0. 0.2, it's still 0. 0.4, it's still 0. 0.6, it's still 0. 0.8, it's still 0. When I get to 1, it's finally 1. At 1.2, it's still 1. 1.4, it's 1. 1.6, it's 1. 1.8 is still 1. 2 finally got to 2. 2.2 is still 2. 2. When do you think it's going to switch? When I actually get to 3. So, what the greatest integer function is doing is it truncates the decimal. And when you truncate something, you just chop it off. So, forget about these for now. So at 1, that's just the whole number 1. But when I get to 1.2, it chops off the 0.2. And you've got 1. At 1.4, it chops off the 0.4, and you've got 1. 1.6, it chops off the 0.6, and you've got 1. Chop. 2, there's no decimal. 2.2, it chops it off. 2.4. So the greatest integer function does not round, it truncates. It chops off all the decimals, and you get the integer that's before it. So when you see these ones, it's 0.8, so the integer chops off the 0.8, and you get the 0. 0.6 is the integer, chop off the decimal. We just never write the 0 in front of the decimal, but that's what so the greatest integer function so 1, 2, 3, 1, 2, 3. So when x is 0, it's 0. All of these ones in here got truncated to 0 until it got to 1. So there's a